We are going to continue our previous thing with some reviews of this Pascal theorem and how we are going to have correspondence to, for example, the simple laws, associative law, distributive law. So we want to make a correspondence between how you understand algebraic statements, simple statements like commutative statement. A B is equal to B, or distributive statement. A into B plus C is equal to AB plus C. So you have an intuition of them in terms of algebra. But how can we have a corresponding intuition in terms of geometry? So you can have a geometrical intuition and try to understand these relations, correspondingly. But from a geometrical intuition. Geometrical intuition in the sense we are going to identify the points which we are constructing in these Euclidean construction. Normally those points we take as numbers and those numbers can have some properties. One is that of addition, the other is that of this thing. For example, when you say AB is equal to BA, so you want to say that, for example, 2 into 3 is equal to
3 into 2.
So what does it mean by that? So addition is
multiplication is commutative.
2 plus 2 plus
2.
So sometimes we say, order of the group will not matter. If you order it this way or the other way, it should not matter in the net scheme of things.
I see.
3 into 2 is equal to 3 times 2. If you order it 2 plus 2 plus 2 one way,
or 3 plus 2.
It should not say. So it will follow from our previous thing. Equals are added to equals. Or equals are added to unequals. If you change the order of that, I think it will not.
The basic.
So the point emphasized is basically the statements you might have studied in your earlier classes, studies about arithmetic. So they can also have independent existence from geometrical statements, and those can be taken from the primitive postulates of this Euclid, or how Hilbert has tried to classify in terms of 5 actions. This is our scheme. In the first case, for example, but in our previous class, we tried to prove that if we are going to use the result
are those postulates true for arithmetic as well as geometry and other systems as well, other disciplines? For example, we study trigonometry or.
No, trigonometry comes in geometry.
I see.
The line, angles, ratios, it's geometry.
So those are general postulates. They are not specifically about geometry.
When you start Euclidean geometry, when you start with Euclidean geometry, actions of Euclidean geometry, geometrical systems, the way we can use algebraic systems.
I see.
So geometrical systems have you identify something as a point in space, how to try to understand space and relations of points in space. What is line? So from that understanding, you have these geometrical systems.
Got it.
But if you define algebraic systems, it's not necessarily you take the course of space. There can be a relationship of algebra and geometry. That you might study in higher classes. But in principle, geometry, how we define geometry and geometrical actions. You can define algebra, and it's not necessarily an algebraic point as should necessarily be identified with a point, geometrical point.
I see.
It is not necessary.
Not necessarily. But there can be some cases, right?
So this is what we are studying. How we define class rational numbers, irrational numbers. Then there is a data card, and there is this how we move of 2 as this.
Say.
So how we can, or even organ diagram, how we just complex numbers. So, but we are going to use our previous notion of understanding of Pascal's theorem that you can identify. There are 2 points which are parallel. There is a third point which is against between 2 points.
They are parallel as well.
So it can also be parallel. So that understanding we are going to use. And how we are going to just say, for example, an algebra of algebra or algebra of say made of 3 points, for example. 3 points, for example, point A, point B, point C. And C can be from the point AC, or C can be identified as addition of A plus B. So you have a line, so it's composed of two line segments, A and
B.
B. Or if you have AB plus
BC.
and sometimes C is equal to
A plus B.
C. So now there are some, for example, so A is equal to AB and B is equal to BC. So if you have some relationships, for example, A is greater than B, B is greater than C, this means A is greater than C. Those relations you can identify as these segments of the line. This A may be greater than B or less than B, or E may be greater than or so this from this
they can be equal.
Identify a relationship, for example, for the segments A and B are said to be smaller than C. In fact, we are writing A is less than C and B is less than C. So, in combined A or B are less than this entire
C. Clear.
So you can have this identification. This line segment or individual line segments are always less than the total line from which these two line segments can be composed.
Fine, it is geometrically clear because we can see it, but algebraically, how is it that true?
So we will go to algebra. When you study actions of algebra, you assume those quantities. So you just need to this time concentrate. If you have defined things like this way, so from this you can, if you identify, for example, two numbers are greater than the third number, the sum of two numbers which is equal to the third number, this means indirectly the sum, for example, 2 plus 3 is 5. 5 is always greater than 2 or greater than 3. But you want to say the same things if you want to identify it in terms of taking geometry as fundamental.
But in vectors, like we have other system of vector algebra, there things are totally different. If we have two vectors and they equal to some other vector, they need not to be smaller than that vector, right? Then the sum.
Sometimes we say that vector algebra is associative or not. It's not sometimes commutative. It is not equal to A cross B is not equal to
B cross A. It's mine.
It's not commutative, something like that. So just orientation. So that's our freedom now, how we define the algebra, the starting assumptions. If the algebra is associative or if the algebra is commutative. If the algebra is commutative or it is
non-commutative. Or
so that's the commutative assumptions. So that's how we construct algebra or how we construct geometry. So in the simplest case, if we have this, we can have identity. We can have this geometrical view of looking at these.
But that's clear.
Greater or smaller.
Yeah.
So if this is this, in the same manner for associative law, for example, A plus B plus C is going to A plus B plus C, and commutative law of A plus B is going to. It's as simple, but still it's like sometimes helpful that if you change it, the order of the group, it doesn't matter. Whether you add it this way or it will again lead to the same thing. It will again lead to the same thing. So this is one.
Sir,
how you have to define in terms of.
Sir, why is not order important there?
Why is
order not important? Now geometrically, as you said, you just right now said that if we just add A to B or B to A, we get the same line segment again. The AC or what you have called C. But I am not. It's not clear to me how that is.
A plus B or B plus A. If you add it this way sequentially, A plus B, but this line segment plus this line segment.
Yeah. Or that line segment plus this
It
line.
will always be the, or from which this line segment was composed of. This is the statement.
But we still have A was on the left side and B was on the right side, and now we are changing it. Now A and we are saying this doesn't matter. Changing the sequence.
Changing the the exact statement would be like that. It's not changing the sequence. So the exact statement is if A is less than C and B is also less than C. So this is the statement.
Yeah.
So I have used my words. I should use the statement. And sorry, this is if A. Sorry, that's not the statement. If A is less than C, it also should mean that B should also be less than C. So I'm just maybe correcting the words.
I see.
Segments A and B are smaller than C. Which, in fact, we will be writing that A is smaller than C. On the other hand, C is larger than C is said to be larger. So I'm just the statement, exact statement is that if C is said to be larger than C. So it's not in that sense. If C is said, if it is said, it may not necessarily.
Yeah.
So that statement.
Achha, we are already presuming that C is greater. C is larger than both the component, both the segments.
So
then we are also saying that whatever is larger in our picture, in our consideration among A, B, and C, whatever is larger, it follows from that it should be larger than all other components. Right.
It should be larger than other components.
But how we reach at that conclusion? How we conclude that? Maybe there can be quantities which are like.
For example, you are saying that instead of using the words monograph and sign, you make algebra of segments. So this algebra of we are using the word, we use algebra of segments word this. So you assume this construction.
Achha.
It is this way. So what I am trying to emphasize is that there is a geometrical way of writing these statements. And how we can articulate them in these things in the first place. So now how we can write commutative law also geometrically? How we can try to understand it from geometrical intuition? So from geometrical intuition...
Even there is also this assumption that we can compare these numbers or these segments. That is also what we are doing. That is an assumption. That we are comparing these line segments. That already means that we are making it relevant, that we can compare these.
We can compare them. Yeah, so we just at the end when we just start so we'll just have a discussion on what is the truth content of geometrical actions. So are they a priori or not? Or are algebraic constructions a priori than that of geometrical constructions?
I see.
So if geometric or geometrical construction can they be constructed a priori? So these questions so that's why in Hilbert's, if you are studying this book, he has used the words between, within. So he discusses at the end what do you mean by between, within. So we are going to take intuitively what he is saying, we are following it.
Sure.
But we can even question those what you are trying to say. Those statements, undefined statements between the statements. What do you mean by between? When you say between 2 points, so what is between? So how can we envision between? Within. So these questions are also as much relevant. So, but we will postpone them in the sense that we are going to, if it's defined this, how can I write simple statements of this commutativity, associativity in terms of geometrical statements?
Sure.
And how we can have conclusions from those things. So in the simplest case, this is commutative. And if you want write, for example, if you want to write how in the reverse construction, if you want to write commutativity of two numbers, we define line segments, and the way we defined previously also. Some line segment is laid off on the in the last process. We define the line, and it's being intersected by
Another line.
1.3 point. The same way we can have two line segments, and on the one side you have B, so you define a point A, and corresponding to define A, we define a unit length on this side.
Yes, sir.
We define a point on this line segment, and corresponding to A, we define a unit length on this thing. Okay? And which is extended to the point B. Then, if we try to meet, so this point AB will give product of this and this.
Can you repeat the statement again?
I'll just read it. So, lay upon the side segment, join extremities and from extremity of B, draw a line parallel to the straight line. Draw a line from the extremity of B, draw a line parallel to the straight line. So if you draw it like this, so if you draw a line and from this line there is an intersecting another line which is perpendicular to this line, you define this
Segment.
which is equivalent to this unit.
I see.
Then from another point B, if you which is parallel to this line, we can arrive at a product AB, which is product of A and product of
Oh.
Product this A and this B.
Yes, this is what it is trying to say. So it will take some time to absorb. And how to define this in terms of how you are going to define this in terms of, for example, Pascal's theorem, for example, and if you define A, and if you define now AB, and you define B, and then again we have this thing, we can define it like this. So we have AB.
I see.
Again, so you have A and you have so you can have this thing. You can have points. You can generate points. It's unit this is and this is point.
Got you.
From this, it's a bit contract or you can show that
I see. All of it follows from Pascal's theorem, right?
So maybe it will take some more time. So let me post just keep it as it is. Okay. Let me take it as you think about it. How if you as an exercise, how if you define this construction, how we can arrive at and also how we can arrive at associativity. For example, A times C is equal to A times or distributivity.
Oh God.
A plus B plus C is equal to A plus B plus
We have already defined that these A, B, C's are line segments, right? Because we need to define that. Because there can be things which are not commutative. So we already defined that it is valid only for segments.
If you have this crisscrossing of lines, you can define B, C. So there are substitute diagrams, substitute two things to this effect. How we can have further these constructions. This and this. Construction A.
Sure.
And this one. So this construction is B. AB is going to be A. Then this. So the point is the way you do in vector algebra also. There is this vector A plus from vector algebra to A plus B plus C is equal to AB plus AC. You've done like this.
Yeah.
But it's from pure geometry.
Yeah, we cannot compare vectors, right? But we are comparing things, so we have to also.
No, I'm not saying as it's not a perfect analogy because this is the basic thing.
Yeah.
Vectors is a vector algebra. It's algebra also. It's not pure geometry. So how purely if you have this constructions and using Pascal's theorem, how can geometrically construct statements which will compare with these things which we know previous course from algebra or from arithmetic. Okay?
Yeah.
So I'll give it as just do it as an exercise because it needs some amount of time and sitting.
Thinking.
Thinking and just then it's
Yeah.
more just first in the first case you need to be familiar with what you see. In the second, third case you just slowly
Try to
absorb it and then get.
say.
So in the same way you can have proportion and theorem of symmetry. Symmetry is using an analogous thing. There is like similar triangles, consonant triangles. This SSA, how are two triangles set to be consonant? How they are set to be similar. These are all statements. But how we can just construct them from the idea of proportionality. Proportionality with regard to how we define these line segments A and B. So if you have two line segments made up of two lines which are constructed of two segments A and B, and you have another line which is constructed of segments A prime, B prime, and if sometimes they intersect at some angle, or they are constructed from two half rays.
I see.
Language of this book, half rays. And how we can make, and then if they make a half ray, then they make an angle. Then you can also make it triangles.
Sure.
So you can make extension or whatever you want to extend. So from given two line segments, you can construct rays, you can construct angles. And how can make the ratios? How can construct ratios out of them? For example, if A, B, A prime, which I was saying, if A, B, there is something called A prime, and this is B prime. So if A, B, and A prime are four line segments, whatever the proportion, such that A prime B is going to A prime. So ratio of these two line segments is equal to ratio of constructed from these two line segments. It is that way. It expresses nothing else than the validity. It expresses nothing else than the validity such that AB prime is going to B prime.
I see.
So actually it's A by B is equal to A prime B. You can say you can have algebraic equivalence. This one, if A by B is equal to A prime by B prime, this means A B prime is equal to, but we have not to think it that way. We have to think it in terms of geometry.
How we arrive at that result?
That's done for exercise.
I see.
For example,
Oh, Khudaya.
in the definition, for example, no two triangles are said to be similar.
Mm-hmm.
When corresponding angles are common. Right?
Mm-hmm.
This new. Now the theorem says that if A, B and A prime, B prime are homologous. So we normally say that they are similar. Homo means similar. But if A, B and A prime are homologous,
In what?
signs of similar terms. It's not equivalent.
I see. If it is perpendicular, it must be perpendicular on this side as well.
If you had some acute angle, on the other will also have acute angle.
Yeah, sure.
So it's not congruent or it's not equal. That's what we
Yeah.
homologous. Almost like the size of similar
Say.
triangles. Then we have a proportion such that A is proportional to B is equal to A prime proportional to
B prime.
B prime. So how we are going to do it? So that so I just running in a diagrammatic fashion. So again, he's using the similar logic to construct a point A and construct a B. And the another point which is constructed from this B, and this A B will represent as product of this
These
A
two.
This here.
This A and B.
This is the point who forms this R. So according to our definition of some product of this line sequence, B is equal to B times B. And B prime is equal to B prime, B prime.
A what?
E prime.
E A prime.
So
I
from this, if you have
take.
divide by this, E is going to be B by A, E is going to be prime by A prime. And from this, you can see that A prime is equal to B prime.
I got you.
This
I
means
got you.
A prime
I got you. B by A is B dash by
So
A.
again, he is like defining it in a way. So you define first this product of, for example, this define product of this AB as modified from this point, and you segment this. The other segment is this. Since this is parallel to this from our previous understanding of
Pascal's theorem.
this will be product of this and
B. Yeah.
But now here define these two.
He is using that here, right?
Because we have not two line segments. This for this, and this for this. This for this. And if they are parallel to each other, you get kind of organization. So AB prime the ratio of this E is B is equal to. Just try to see it is.
Yeah,
And
yeah.
then he extends this logic to other states. Just try to read it.
Sure.
Mix a bit of. And now the same argument he is constructing equations of straight lines and of planes. So we can extend this argument not only for angles, but also for straight lines and planes. So if there are straight lines, for example, with a simple equation of straight lines, y is equal to mx plus
C.
you can have or ax plus by plus
C.
c is the equation of straight line. So if a straight line, for example, if a straight line, the straight line, for example, is how can so if a straight line is constructed such that, for example, there are particular propositions. For example, a into 1 should be equal to, and if a into b is equal to 0, it means either a should be 0
Or B should be
or
0. B should be 0.
yes, yes. But you have to think in terms of some line segments. These are 2 line segments. So you have not to have the algebraic intuition. You have to have geometrical intuition.
Got it.
So that's
That is clear.
that's to be emphasized. So you have not to have that.
Because again, it raises a lot of
some
questions.
arithmetic.
Yeah,
You have to have
Geometric.
probabilities of geometry. Imagine it. That's
By 1 we mean a line segment which has a length of 1, right?
If
Geometrically, how to think of 1?
if you study a line segment which is multiplied by identity. Identity means it's ones. So in the other case, it's the order of identities from this to this. The other is from reverse. So it will not it should be the same. If you start line segment from this to this or this to this. But
Geometrically, how I understand? See, right? We are multiplying. The operation is multiplication there. It's a multiplication operation. How to understand multiplication in terms of lines or geometry broadly?
you're right, but here what he is saying, if you use also which is determined by single point and make appropriate conversion, then all of the rules reduce from 13. Rules reduce from 13.
We go now 2 into 3, and we know that it is 2, 3 times
So
2
if
plus
you
2.
remember when we studied theory of proportions, we studied theorems of order. Theorems of order means if A is greater than B, B is greater than C, this means A is greater than C. If you just scratch that, move back.
Yeah. That's understand. I'm talking about the multiplication process. What is rightly happening? You just gave an example: 2 multiplied by 3, and it is 2 plus 2 plus 2, and I can.
He's saying this, if we introduce also segments which is determined by single point, make other appropriate conventions, then all other rules for calculating the real numbers will also hold for here for calculating. So it is making inference.
I see.
It's not making a statement. It's different between statement and inference. So inference means that if you can do the same thing for numbers, algebra, for example, which is determined by
Real numbers.
calculating the real. If you do the same thing for by calculating the real numbers, will hold equally for calculating the segments.
I see.
So he is not making a prior statement. He is making this thing.
So we are more specifically talking about geometry, which includes real.
If we can do something for algebra, if you do the same thing for geometry, it should also hold. This is what he is saying.
Oh God.
So if you construct an operation which can be true for algebra, what
That must be true for a geometry.
Geometry. He is not.
It should have a corresponding geometry, right?
That is equally true for geometry.
Acha.
That calculation is true equally for geometry. This is what he is saying.
I see.
But why it should be true? He is not just.
Justifying.
But then the question also is why it should be true for algebra also.
Yeah. Yeah.
So again, so an approach operation we have defined in algebra is also we are using it here also.
Sure, sure, sure. It's very important. How are we able to do that?
And if A is greater than B and C is greater than 0, then AC is always greater than BC. If A is greater than B, C is greater than B, AC is greater than
C is greater than
0.
0. Okay.
So if A is greater than B, C is greater than, so A into C is always greater than B
B
into
into
C.
C.
You can have the inclusion of
So fine. Look, we can extrapolate the what we have done in arithmetic holds for or algebra holds for geometry as well. Fine. But it seems more intuitively we can understand what is happening there. Like 2 multiplied by 3, you just explained that it is 2 plus 2 plus 2 and understood. What multiplication is doing is basically adding on.
repetitively adding.
Yeah, but here it is not really clear what is really happening when you are multiplying one segment A with one. How to geometrically see it, and what we mean by A multiplied by B is equal to 0. How to see it geometrically?
How to geometrically.
Now I see 2 multiplied by 0 is 2 times 2 0 like it. It is 0.
Then you have a quantitative understanding of things. You see, so define. So you postpone this question. This is a valid question, and try to understand. When we just try to, for example, what is known as spatial intrusion. So there comes again this question of, for example, how do you try to imagine space? And you presume that operations in space should hold. So it's a given question whether the space is intrinsically, for example, we have some properties like isometry of space, translation in space, for example, in the actions of geometry. You can read foundations of geometry by Burton Russell. It's a good text. Somewhere he writes that, for example, if a person, there are 2 books in the room. The 2 books are in the same dimension. X, Y, and Z. X, Y, and Z, for example. So another book is on the same that book.
Fine.
So a person comes into the room and he sees one book. Both of the color of the books is black.
Identical.
So you cannot identify
Which one is
blue and which is above. But if their color is same, you cannot identify.
Yeah.
But once if you change, if it's black and white, if you change their border, it doesn't matter for external matter. But if the same person comes again, if the color of the book is different, one was red and one was blue, and you just change it the place. The other person is somebody has come, he has changed the.
He can observe that.
He can point out.
Yeah.
But in the earlier case, he was not able to point out.
Yeah.
So this means you have an intrinsic idea of space.
Yeah.
That space doesn't fundamentally change when you translate things from one point to another point. So whether this axiom is something called axiom of viability or axiom of transfer, some axiom it's called in geometry. We presume that once you translate an operation, the intrinsic character of the space doesn't change, or measurement doesn't change. So here you can see it. Whether this commutativity should really hold or not for a space. If space is isometric, so if you change, it doesn't change. But if you define space in some another way, maybe these operations may not hold. You define these things. So you go from one space to another space. So it's a big discussion. We'll come to it at the end when we try to discuss the geometrical axioms, how they are similar to algebraic axioms. So Maybe, but in the first place, we assume that if you, some algebraic operations which hold for algebra, it will also hold for geometry.
But
If
okay,
it will not
we're not at that level right now, but there must
it
be
will not lead to
strong
any
foundation.
contradiction. It doesn't lead to any contradictions. That's the point. It's not to necessarily to go to philosophy of the things or to go to the prior assumptions. So in implications, that is lead to any contradiction or not.
Acha.
So if you define geometrical statements and identify them with these things,
Logic remains consistent.
so does it lead? So you are able to do something. This thing. So if it leads to some contradiction in some theorem, then our prior statement doesn't follow.
Oh, no.
So this means if it holds an operation holds for arithmetic, it's also equally holds for geometry. Because it has not led to any, you can do many things by that way. But it's also another question if the prior actions of geometry can have value. So this is a good section of Buddha's book.
Great. What geometry, no?
Foundation of geometry. So maybe I just do for the straight line also uses similar intuitions for straight lines. So if you define that, so again for straight lines also he is using the symbol. Just take it. So now one important point which I would like to emphasize is that for example, so if we for example if we first select a straight line with 2 points, for example 0 and 1, and we bisect them, for example there is some, can always between 2 points there is always a given point. You can always construct a point 1 by 2.
Say.
You can construct a point 1 by 2.
Barabar.
1 by
8.
so on. So between 2 points you can construct number from 0 to 2, for example, of you can have 1 by 2. You know?
Say.
And so on and so forth. So you can construct 0 times.
Barabar.
Or you can construct the same if it's from this side of the line. You can also construct it from
Other side of the line.
Or you can say it's n by 1 by 2 reduced over n. So it's, if it's on one side this, the other side it will be n by 2 over n.
Okay, so we are now making the measurement from midpoint of the line, right?
So it means it's to make home to the point, if you remember the actions of order of this previous tutorials. So there can always be a constructed point line point which is theory of succession.
Yeah. That
Between 2 points there can be, you can let
we can always have another point.
So then among this, there always exists a certain point A and such that B lies between A and A. So if A1, A2, A or A1,
Yeah.
so there will always exist a point B which will exist between
these 2 points.
but which is lying in that whole system of points.
Yeah.
So if you want to write it in terms of for example A, B, C are 3 points of straight lines, and if you want to make it corresponds to the algebra, and alpha, beta, gamma are the real numbers, and B lies between A and C, then one of the inequalities is always fulfilled. Alpha is less than beta is less than gamma, or alpha is greater than beta is greater than it's always fulfilled.
Can
every number belongs to field of, so here it is making a bit of correspondence between algebra and geometry.
can you repeat from there again, please?
So for example, if
A, B, C, but
A, B, C are any 3 points of the straight line,
here.
and alpha, beta, gamma are the corresponding real numbers.
अच्छा ठीक है.
And if B lies between A and
C.
then one of the inequalities always fulfilled. Either
Okay.
this is fulfilled or either in the succession, you move for greater thing, or
You come.
if you move from this side of the point, for example, A and B is from
This is less than this, and this is less than this, or this is greater than this, and this is greater than this. Yeah.
The reverse word.
Yeah.
So here's at the end trying to be a reference of geometry and algebra. This is what you can identify a point, geometrical point with the corresponding algebraic construction. Even though he has used the statement that it's not always true. For example, if there come irrational numbers, so how we can? You cannot have between two numbers. You can always have a 1 and 0, 1 by 2. But once there are irrational numbers, how can you locate it? You have to find that root 2 is also it can also lie on a number now.
Yeah.
Because when you talk of irrational numbers, they are non-terminating, non-recurring. You cannot, but you have to show it should lie on the
God. Yeah.
number line.
It doesn't.
So this is true for simple
Real numbers.
irrational numbers. But if you also include irrational numbers, you have to.
It's like it cannot. Apparently, it seems. It may not be true. Apparently, it seems because it's not non-terminating and recurring. We cannot locate it.
So that's another. You can do this same statement if you read this sentence. Again, but from you have to show that root 2 is a rational number. Irrational number falls on the number line. If it falls on the number line, then this statement is further. But for general rational numbers, it holds. But it can also hold for rational or general real numbers, but you need more construction. For that, you need to show that root 2 or irrational numbers also exists on the number line. For that, there is this theorem. So, but here, the simple point is you can make a correspondence between a geometrical point and an algebraic
I see.
number.
Yeah. That's important.
Okay.
यही तो हम ऊपर बात कर रहे थे.
So basically, one thing remains that you should go for displaying other constructions. Try to see it in place. And try to see it in the context of Pascal's theorem.
Pascal's theorem.
These statements. That's at least a bit more amount of time. Okay, so we'll stop.
Great. Thanks. Thank you so much. It was really beautiful.